For my hybridization project, I chose the molecule phosphate. In order to understand the hybridization of phosphate, we first need some background information. So what is phosphate? Phosphate is a polyatomic ion or radical. To clear up, a polyatomic ion is a group of atoms bonded together with an overall charge. This radical consists of one phosphorus as a central atom and 4 oxygen as the surrounding atoms. Since this is a polyatomic ion, it has an ionic charge of -3. The next step towards understanding the hybridization of phosphate is to analyze the structure of the radical, more specifically a Lewis dot diagram. You can notice that there is one central phosphorus atom and 4 surrounding oxygen atoms. The goal is to understand how each of these atoms will bond. To start, we will use our need-have method. Phosphorus needs a full octet of 8 electrons. Oxygen needs a full octet of 8 electrons times 4. In total, this will give us 40 electrons. Now let's talk about how many electrons we have. Phosphorus has 5 valence electrons, and each oxygen atom has 6 valence electrons times 4. And lastly, let's not forget about the ionic charge, as it is a polyatomic ion. Hence, we add 3. This gives us a total of 32 electrons. Finally, to solve for the number of bonds, we take the difference between our need and have numbers, then divide by 2, due to each bond representing 2 electrons. This gives us a total of 4 bonds. Upon applying these bonds to our diagram, we notice that the central atom only has single bonds to each of its surrounding atoms. Remember that each of the surrounding atoms needs a full octet, so we will now draw in each of the pairs of electrons. As we draw, you will notice that the central atom does not have any drawn in electrons. This is because the bonds connecting phosphorus to the surrounding atoms already fulfills the octet requirement. Next, we will look at our finalized Lewis dot diagram. It is pretty much identical to the previous, the only change being the addition of the overall charge of -3, as this is a radical. Our next step is to understand the electron configuration for the central atom, phosphorus, using our periodic table method. To do this, we will go in order of the elements until we hit phosphorus. So now we know we have 1s2, 2s2, 2p6, 3p2, and 3p3. Writing this down, our regular electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p3. However, we want to shorten this. We will take the previous energy levels where the last electron is not located and replace it with the nearest previous noble gas. In this case, it is neon. The condensed electron configuration will now be open square bracket Ne close square bracket 3s2 3p3. However, remember that this is a radical with a charge of -3. Hence, we have to add our ionic charge. Therefore, phosphorus 3 negative will have the electron configuration of open bracket Ne close bracket 3s2 3p6. Now to visualize this, let's put it into our condensed energy level diagram. Looking at our condensed electron configuration, open bracket Ne close bracket 3s2 3p6, we will organize our chart in rising potential energy. Due to this being a condensed energy level diagram, similar to the condensed electron configuration, we will start with the nearest previous noble gas. In this case, it is neon. Now we have 1 3s orbital and 3 3p orbitals. To complete this diagram, we will be drawing in the electrons from our condensed electron configuration. Using Aufbau principle, Hund's rule, and the Pauli exclusion principle, we know that the lowest energy orbitals are filled first. That in the case of multiple orbitals of equal energy, each orbital gets a single electron before pairing up electrons. that when two electrons are in the same orbital, these electrons will spin in different directions. However, this is a polyatomic ion. We know that we gained 3 electrons due to this representing phosphate. Hence, to show that we gained 3 electrons, we will be using a different color to represent it. Finally, let's create a hybridization chart. For the last time, observe our Lewis dot diagram. Notice that there are 4 single bonds. However, these single bonds can be categorized as sigma or coordinate covalent or CCBs. In this case, we have 4 CCBs, as the valence electrons for the surrounding atoms are equal to the number of electrons not in the bonds. In the chart, each CCB is represented by a hybridized orbital and a pair of arrows. To complete this chart, we simply have to draw in the arrows. To name this, we know that 1 s orbital and 3 p orbitals have been taken over. So we will write 1s, 3p, the superscript indicating that 3 p orbitals are filled. To finish, we know that our last electron level was level 3 from our condensed energy level diagram. Therefore, we put the number 3. An intramolecular force is any force that binds together the atoms composing a molecule or compound. This is not to be confused with intermolecular forces, which are forces between molecules. Examples of intramolecular forces include ionic bonds, which are bonds between oppositely charged ions, nonpolar covalent bonds, which are bonds that are formed when electrons are shared equally between 2 atoms in a compound or molecule, and polar covalent bonds, which are bonds that are formed when electrons are shared unequally between 2 atoms in a compound or molecule. The intramolecular forces in a molecule determine whether a molecule is polar or nonpolar. To identify whether the polyatomic ion phosphate is ionic, polar, or nonpolar, we can do a quick calculation of the electronegativity difference between the atoms in the ion. Phosphate has 2 different types of atoms in its structure. It is composed of 1 phosphorus and 4 oxygen atoms. Therefore, the 2 different atoms in phosphate are phosphorus and oxygen. To complete the electronegativity difference between the 2 atoms in the ion, all we have to do is subtract the electronegativity of the oxygen by the electronegativity of the phosphorus, giving you the electronegativity of the phosphate ion. The electronegativity of oxygen is around 3.5, and the electronegativity of phosphorus is around 2.1. If we find the difference between the two, we get 1.4, the electronegativity of phosphate. According to the chart, 1.4 is between 0.4 and 1.7. Thus, we can say that phosphate is a polar molecule. As said before, phosphate has 4 CCBs, or coordinate covalent bonds. A coordinate covalent bond is a shared bond between 2 nonmetals, in which one of those nonmetals will unequally share its electrons with the other. In this case, we can clearly see phosphate doing so. Phosphate is a polar ion. Due to this, we know that polar ions have an uneven distribution of electrons that result in a positive charge at one end and a negative charge at the other end. Additionally, since phosphate is polar, its intramolecular forces will be strong. Since phosphate's ions attract each other strongly with opposite poles, phosphate is usually in a solid state of matter at 20 degrees Celsius. Finally, the last physical property of phosphate is that it's soluble in water. This is again due to the fact that it is polar. The partial negative part of one polar molecule, like water, will interact with the partial positive part of another polar molecule, like phosphate, resulting in polar substances dissolving in each other.